Okay, today is March 3rd, 2022, and summary of Gauss's law that I have here. Gauss's law applies only to problems that have symmetry. We have seen problems with spherical symmetry and cylindrical symmetry. Problems that have spherical symmetry are problems such like the one of the point charge and the spherical charge distribution. Problems with cylindrical symmetry are infinite linear charge distribution, infinite cylindrical charge distribution, and infinite planar charge distribution. Steps to solve the problems. Solve problems using Gauss's law. Steps to solve problems using Gauss's law. Here you go. First, I identify the problem has symmetry, either cylindrical or spherical. Identify if the charge distribution has symmetry. If you have a spherical charge distribution, okay, that's uniform charge distribution, this problem will have spherical symmetry. If you have, again, a spherical charge distribution with increasing charge distribution from the center to the surface of the sphere, that also will have spherical symmetry. However, if the sphere has more charge on one side of the sphere and less charge on the other side of the sphere, this problem will not have spherical symmetry. That we have to solve this type of problem, you have to apply something else other than the Gauss's law. Come up with a qualitative behavior of the electric field. Positive charges generating a field that's away from the charge. Negative charge generates field that's towards the charge distribution. So you have to have a qualitative idea of how the electric field behaves around that charge. And I showed to you how you can come up with that. Just apply Coulomb's law, right? It's a qualitative solution, but it's not a quantitative solution. But you need to have a qualitative knowledge of how the electric field behaves around your charge. Surround the charge distribution with an imaginary closed surface. That's what we call the Gaussian surface. The Gaussian surface is going to be either spherical or cylindrical. That's what we did here. The electric field will be either parallel or perpendicular to the area vector of the surface. Okay, let's put the surfaces. Okay, sometimes we have more than one surface, right? Like the cylindrical surface, we have the cylindrical, like a closed cylinder, right? You're gonna have the cylindrical surface here, and you have the two caps. In this case, your cylinder is made up of three open surfaces of the surfaces. Solve the integral for the flux. That should be easy if you have just fields that are either parallel or perpendicular to the area vector. The integral of the flux will depend on the unknown electric field. So for the enclosed charges, for the charge enclosed by the Gaussian surface, Q enclosed, and determine the electric field from the two sides of the equation. That's how we solve this type of problem using Gaussian distribution. Let's see if we did everything that we could have done. Here we go. Yeah, we did everything. Okay, so let's write it down. What were the charge distributions that we work with? Again, I have a list there in the back, right? I just want to, here we go. Charge distributions. Point charge. We did the electric field of the point charge. We solve the electric field of the point charge using Gauss's law. Uniform spherical distribution of charges. The spherical shell of charge Q and radius R. Let's see, uniform spherical charge, net charge Q and radius R. Infinitely long rod with a uniform charge distribution. Let's see, I'm going to put also uniform, right? Spherical charge distribution, spherical shell. Spherical shell with a uniform distribution of charge. Here you go, let's do it this way. Spherical shell with a uniform charge distribution. Charge distribution. I don't need to put those Q and R. Let me take it out. Yeah, there's no need for that. That's redundant information. Uniform spherical distribution of charge. The spherical shell is a uniform charge distribution. What else? Infinitely long rod with a... Those are the problems that we solved. Okay, there are more out there. There are more out there. Infinitely long rod with uniform charge distribution. The charge, in all those cases, the charge doesn't have to be uniform, provided that the charge distribution has symmetry. Okay? You can have, for instance, a rod with very little charge here at the middle, and the charge, amount of charge keep on increasing, symmetrically around the center of the rod. You can have that. That would be considered a uniform charge distribution. Infinitely long cylinder of radius r. Okay. Infinitely long cylinder. Let me see. Solids. Infinitely long solid cylinder. Okay. Another one that we did, infinitely long cylindrical shell. We did that as well. What else? Let's go here. All right. Here's the sphere, right? Let's see here. Yeah, that's the point. I have more drawings that I need than what I need. Yeah, here you go. That's what I did last time. Yeah, that's the point charge. That's the point charge. That's the spherical charge. Uniformly distributed spherical charge. Uniform distribution. Here's the shell, spherical shell. Inside and outside. Then we start with the cylindrical distribution. Up to now was spherical distribution, right? Spherical symmetry. Then we do this one, is the rod. One-dimensional rod. Charged rod. Okay. Then we did the solid cylinder. Inside and outside, the cylindrical shell, right? And then we did the infinitely long planar distribution. Here you go. Infinitely long planar distribution of charges. So 7 different types of problems that we treated here using Gauss's law. Problems we solved using Gauss's law. Okay. So we are done with this chapter. Done with chapter 24. Let's see if we can take a look. How is our syllabus here going? P38 syllabus, P21, P38 spring. Okay, that's the one I want. Let's see if we can get it. Let's see how is our schedule here. Okay, everybody is having access to the homework. Yeah, no problem with the access to the homework. Here we go. Let's take a look here. How we're doing. Gauss's law. Today is the 3rd. So we're a little bit behind. Oh no, not a little bit behind. We're almost the same, yeah. So today we're going to start electric potential. Okay, now the electric field 1 lab, right? For the electric field 1. I didn't put the due date. Huh, interesting. Okay, those two are due on Tuesday, March 8th, right? March 8th. Due March 8th. This one also is due. I gave you until March 8th to do that. So you have plenty of time to prepare it. Right? Now, what about this one? Resistance. I'm not gonna put the amount, resistance measurement only. Better like that. Do 15th, March 15th. Next, do 22nd. Do 22nd. Single. I'm gonna put single resistor here. Uh, Then you have two resistors. It's gonna do on 19, 22nd. No, this one you don't have to turn in on 22nd. Can turn in on April 12th because you have an exam, right? And then you have a holiday. April 12th. It's okay to turn in April 12th. This one is going to be due to, let's see, two resistors. Due when? April 19th. Due. Some small adjustments here. This guy here is going to be due 1926. No, it's not 26. It's going to be later. May 3rd, because we have an exam, right? If we change the exam, this date is going to be changed as well. Flashlight bulb. It's going to be due May 3rd, May 10th. May 10th. Okay. The other one should be May 17th. The diodes. That should be May 24th. Yeah, May 24th. Okay, yeah, let's do this way. And that's going to be my version version 4. I'm not gonna upload that yet, but you see what's the deal here, right? So what you're going to do now, you're going to do electric potential. Notice that we did those experiments dealing with a concept that we hadn't covered in the classroom, right? Electric potential happens only now. Start covering electrical potential only now. And yet we did an experiment before we covered the concept, the idea. That's because we do not have enough equipment to do the other experiments, okay? That's why. Ideally, we should be doing experiments with electric charge initially. Ideally, we should be doing experiments with Coulomb's law. That would be the idea, but we don't have equipment to do that. So instead, we start with experiments on the electric field that use the idea of the electric potential. Okay. So the story goes like that. Summary again. I like to keep on going back to those summaries. So here you go. Donors chapter 24, right? So what did we do? Electric charges, right? Then we did electric force. Then we did electric field. That's what we did so far. And now we are going to talk about electric potential energy. And after talking about electric potential energy, we are going to talk about the electric potential. If we were to make a parallel between what we have right now and what we did in mechanics, I'm gonna make here a table for you. Concept, right? I'm gonna do like that. Yeah, let's do this way. Let's see. Source. I'm gonna put like that. Gravitational. Source of the gravitational field and the electric. The source of a gravitational field is the mass. The source of an electric field is the electric charge. Okay? So here we can say that the mass is what we may call the gravitational charge, right? Could call it like that. If we call that electric charge, then this one we can call gravitational charge. Or we could call it in a different way. We just call, let's say, gravitational mass. Here we would call electric mass, right? It could go both ways if you were to rename it, all that stuff. Okay, what about the force? Okay, we have the gravitational force, and you have the gravitational and the electric force. Let's put it here. Gravitational force and electric force. And then here we can write it down, field. What's the field? What is the gravitational field? The gravitational field is the acceleration of gravity, right? And here we just call the electric field. The acceleration of gravity is the gravitational field. The gravitational field is the acceleration of gravity. What else? Then we can go the next step. Potential energy. Okay, so we have the gravitational potential energy. And here we have what? We have the electric potential energy. In the same way that we obtain the gravitational potential energy, we are going to obtain the electric potential energy as well. And then there is something that we define in electricity that we don't define in the gravitational theory. Electric potential, yeah. But what's the electric potential? It's very easy. Okay, I'm going to explain that to you. Here we can call, there is the gravitational potential, and then there is the gravitational, there's the gravitational potential energy, and then there is the gravitational potential. We never covered that in mechanics, but it's possible to define the gravitational potential. Okay, and that's the concept. That's the idea that is easier to measure in the laboratory. The electric potential is far easier to measure than the electric field. Okay? And there is a relation between those two. Okay? So let's write it down. The electric potential is far easier to measure in the laboratory than the electric field. And that's the progression. We have a similar progression in mechanics. Okay, first we talk about the mass, then we talk about the gravitational force, then you talk about the acceleration of gravity, then you talk about the gravitational potential energy. We don't talk about the gravitational potential, but it follows rather easily. Okay, I'm going to show you how it follows. And we are going to concentrate now on those two ideas. Okay, at this point you should know how to calculate the gravitational potential energy. If you know how to calculate the gravitational potential energy, it's going to be very easy for you to understand how to calculate the electric potential energy. Okay? So here you go. Let me give you an example again. When I raise this bottle against the gravitational field, what am I doing? I am pumping gravitational potential energy into this guy. Energy has no mass. The mass of this bottle doesn't increase. Okay? And now this bottle has some gravitational potential energy that, if you are smart enough, you can use this gravitational potential energy to do some useful work for you. Okay? That's we can, for instance, convert this gravitational potential energy into electricity. People do that. We can convert this gravitational potential energy into kinetic energy. People do that. There are devices out there that take advantage of the gravitational potential energy. Okay? And what about the electric potential energy? How can we come up, how can we explain that? Let me see if I have an illustration here for you. Okay? Think about two electric charges, one positive and the other negative. Okay? Here you go. Here you go. That's a good illustration. When you are talking about gravitational potential energy, we are talking about two masses. Let's say one smaller mass and another larger mass, the bottle and the earth. This guy has gravitational potential energy because the earth is part of his system. Without the earth, this mass has no gravitational potential energy whatsoever. Make sense? The same thing can be said about the electric potential energy. Let's say we have this negative charge that's big and a smaller positive charge that's a given distance from this negative charge. Okay? Big charge here, negative charge here, smaller charge here. They attract one another, right? They attract one another, just like in the case of the gravitational potential energy. So this small charge tends to move towards the bigger charge, the bigger negative charge. It means that there is a electric potential energy between those two charges. That's what it means. If I hold those two charges in place, there is potential energy, electric potential energy. If I release them and they collide with one another, stay stuck, then there is no more potential energy in the system. That's how you gotta think. That's the example for positive and negative charges. But I can give you also an example for two charges with the same sign. Let me give you an example for two charges with the same sign. Okay? So here you go. I'm gonna hold a positive charge on my hand and another positive charge on my hand, on the other hand. Okay? And I'm going to bring them closer and closer apart. Okay? Closer and closer apart. There is no gravitational analogous for something like that because masses they don't repel each other. Okay? But there is a case for charge. For masses, there is no analogous for that. And the closer I bring them, the harder it becomes to make them come closer together, right? Because they're repelling each other. While I hold them at this given distance, they are holding an electric potential energy. The system holds our electric potential energy. We subtract one of the charges, this charge has no potential energy whatsoever. Potential energy exists only whenever you have at least two objects together. Electric potential energy exists only whenever you have two electric charges together. Gravitational potential energy also exists only if you have two masses that are interacting with one another. Okay? That's the important idea of gravitational potential energy. You have to have at least two objects interacting with one another. Okay, so the moment I release those two charges, they just fly away because they have potential energy to do that. Their potential energy is converted into kinetic energy. Okay, that's the idea that you have to have about potential energy. Now, you may have electric potential energy not just with two charges, but with three charges. This system, if you consider a system with three charges, because a system with two charges has potential energy, but a system with three charges also has potential energy. Okay? And how is the potential energy calculated? The net potential energy of the system is going to be the potential energy between those two charges, the potential energy between those two charges, and the potential energy between those two charges. That's what's going to be the net potential energy of the system. Think about that. Here we are talking in terms of electric charge, but think about that in terms not just in terms of electric charge, but in terms of molecules in your gallon of gasoline. Okay, your molecules in your gallon of gasoline has electric charges in them, and they have a bunch of electric charges in there. They have a bunch of molecules of gasoline in there, and they are all interacting with one another through the electric field. So your gallon of gasoline has some potential energy there inside. Okay? And then people finally figure out a way to tap into that potential energy of the gasoline. We what do we do to tap in the potential energy of that gasoline? We use a internal combustion engine. We use the engine that we have in our car. Okay? So they are tapping the potential energy of the gasoline to make some useful work. That's the whole idea of potential energy. Okay? So here we go. Let me see if I can. Yeah. So now, mathematically, how does it translate mathematically? Okay? Electric potential energy. Start with electric potential energy. Okay? Remember, you know, the idea of electric potential, the idea of potential energy, whether it's gravitational potential energy or electric potential energy, comes from the idea of work, right? Remember that? Let's write down the idea of work. So in order for you to understand potential energy, you have to remember the idea of work. Let's write that down, you know, how work is defined, right? Work is defined in terms of a line integral. I'm going to write here the line integral. Work of a given force F. Let's see here, equation. You know what? I'm going to get that E that I got here. It's okay. It's going to take forever. I hate that. I'm going to get here. Here you go. The vector, that's I'm being very specific, is work of a vector, right? Work is always the work of a force, work of a given force, and it is what? Oh, it's not E, it's F. Work done by a force. Work done by a force is what? Is the line integral of dot dr, right? Remember that? We're using all the same concept that we used before in mechanics. Here you go, f dot dr. Remember that? And there is more to it, right? Since we're integrating the vector, the limits should also be in terms of a vector. Initial position, the final position. That's how. That was the definition of force. Okay? Definition of work, right? Definition of work of a given force. Here we go. Then, for certain, I'm just reviewing what we saw in physics 37. For certain types of forces, it is also possible to define what we call the potential energy. Okay? What's the name of those forces? Which forces has a potential energy? These forces are called what? Conservative forces. Okay? So far you know how many types of conservative force. You know only three, right? You know the gravitational force at this. And here you go. Conservative forces that you already know. Conservative forces that you already know. The gravitational force nearby their surface. Okay, this gravitational force is gonna be what? F equal to mg. Hooke's law. Hooke's law. F equal to minus kx. Those are all vectors. Gravitational force in general. F equal to big G. Oh, gotta have a negative there. Big M, small m, r squared, right? Those are the three conservative forces that you already know. Here you go. Now there is another conservative force. You must know. I can prove that to you. The electric force. The electric force is also conservative. The electric force. Okay. The electric force is also conservative. Unless you write the electric force. You can prove that mathematically. I'm not gonna prove it. Okay, but it's, so you have to take that for take my word for that. And I have a hat here. Okay. I didn't put the notation right. Force of one, here you go, of 1 in 2, right? I have to, let's do the notation like that. Whoa, 2, right? And what else? Force of 1 in 2, vector position from 1 to 2. That's a better notation. There's no positive or negative here. Just be reminded that the gravitational force is like that. Has a similar notation, right? Gravitational force is going to be like that. Big G, M1, M2, okay? But the only difference is that we have a negative sign here. That's for the gravitational force. So how do we calculate? So how do we calculate the potential energy between two electric charges? Okay, we calculate in the same way. In the same way, we calculated the potential energy between two masses. Okay, here we go. Potential energy between two charges. Go, it's going to be like that. Delta U between charges 1 and 2, right? Is equal to what? Is equal to minus this integral here. Is equal to minus this integral. Let's not forget 1, 2. And by the way, should this dr also should be 1, 2. I'm not gonna complicate this notation. Let's leave it this way. Let me see if I have illustration for you. No, I don't have an illustration. Oh, shame. Yeah, I don't have an illustration for that, unfortunately. Okay. Don't forget, this, what you see right in here is the change in potential energy. And you can calculate the change in potential energy only when one charge is moving with respect to the second one. So you have the change in potential energy between charge 1 and 2, okay, is given by, the difference in potential energy is given by this integral when one of the charges move from one point, the initial position, to a second position, okay? The potential energy is always calculate in terms of difference in potential energy. We're not, there is no such a thing as potential energy. What there is the difference in potential energy. That's the key idea, okay? It happens that for certain specific conditions, if you impose certain specific conditions, we just drop the term difference in potential energy and keep on calling potential energy. That's it, okay? So that's how we do it. And I'm gonna drop also those subscript. Let's see, to make the notation simpler. Uh, let's see. No, he doesn't like it. Okay. So that's it. Ah, that's hard. Hmm. Huh. Interesting, huh? Hey, yeah, this guy sometimes does that to us. See that? Now he's doing italics. Huh. Interesting. We never figure out why he behaves this way. So now I'm going to write that down in a notation that's simpler. Okay. I'm gonna drop the subscript 1, 2 to simplify our notation. What time is that? That's 5:45. Let's take a break right now, and I'll take attendance, and we go for a 15-minute break, and we continue this derivation here. Let's see, Excel. Lecture attendance. Today is March 3rd. Huh. 7, 7.9, 14, yes. 14. Mário Acevedo? No. Toby? There. Harun? Musa? Musa here? No? Yeah, raise your hand, Musa. You can't hear it. He's there in the back? Oh. So it looks like he's doing something really important. Genesis? Genesis? No? Uh, Jennifer? No, Jennifer. Let's see, next. Robert Faust. Here. Pedro Flores. Lawrence Flores. Lawrence? Not here? Lawrence Flores. Alexander Garcia. Sung. Brian Indias. Athena. Dylan Martinez. Rafael Mercado. Alexis Nigret. Abraham Perez. No. Nicolas Pisano. No, never came in. Ramon Quintana. Ali. No Ali. Kenny Villagomez. Patrick Villavazov. And Nolan Williams. Let's see how many people we have here. 14. Yeah, call it. Okay, good. 14. And we are gonna have our break right now. 5:51 to 6:06. Break till 6:06. I'm gonna pause here, okay? Remind me to turn it on when I come back. So we're gonna calculate the potential, electric potential energy, which is minus the work done by the electric force. And what drawing that you have to have in mind? The drawing that you have to have in mind, I'm gonna make it right here, one for you right in here. Okay, so we're gonna have one charge. I'm gonna use this drawing here. Yeah, let's use this drawing here so I can save some time. Here you go. So let's say it doesn't have to be a charge that's much larger or much smaller. Okay? So let's see, we have one charge. We have two charges, right? Oops. Here you go. Move it. So let's say this charge is initially at this position. I'm gonna put an initial vector position. Here you go. Initial vector position. I'm not even, it doesn't, we don't even have to put a sign to the charges, okay? Let's do that without a sign. Here you go. Vector position here. So we can do it in the most generic way. Here you go. That's what I call the initial vector position, R0. I'm gonna get that here. And because we're talking about a conservative force, the work done by a conservative force doesn't depend on the past. Remember that? The electric force is a conservative force. And because of that, okay, that's the initial position of charge Q. Oops. What is this thing here? Do you see that thing in there? Yeah, do you see this little thing? What's that? Must be a little point that was in there. Okay, and then we have, let me increase the size so everything becomes, yeah, font size, right? So this charge is then moved from one place to another one. Okay, the path doesn't matter because it is a conservative force. Because of that, I'm not even going to show what the path is. And this vector is taking with respect to this origin here at the center of the other charge, initial position and final position. That's the drawing that you must have in mind when you're calculating that integral. Okay? Doesn't matter, again, doesn't matter what the path that the charge took, because the force is a conservative one, can be whatever path you want, here you go. So that's the equation, that's the drawing that you have to keep in mind whenever you're going to solve this problem here. Okay, and now I'm going to replace this equation. Oh, what happened here? That's okay. Yeah, here you go. This guy right in here. I'm gonna replace right in here. And I'm gonna change the notation. Big Q, small q. Okay, the vector position is taken from the big Q to the small q. Yeah, here you go. So we go ahead and take out the constants out of the integral. We are taking this dot product r hat dot dr. Dr is not necessarily in the radial direction, okay? Dr initially is varying in this position, I know, is in this direction. Dr is tangent to this path. That's what Dr is. Dr is tangent to this path. So it doesn't necessarily have the radial direction, the Dr, although it's the same letter that we use. Ideally, we should be using ds, okay? That would be the ideal way. Yeah, let's use ds instead, so you don't mix up the r hat with the r vector. That's a better notation. When we take this dot product, what we get? We get dr, okay? Because the ds can have all sorts of components, 3 components, right? If it's spherical coordinate system, it's going to be r hat, theta hat, and phi hat. The only thing that survives is the dr in the r direction. And now we can, and when we change the integration variable here, we also have to change the limits. The limits are no longer vectors. And then we go the next step, which is to solve this integral. This integral is easy to solve, right? This integral is 1 over r, but it is a negative r. R naught. Here you go. This is exactly what we did in mechanics. Here you go. That's the one I want. And then I gotta put that guy in. Minus 1 over r. Here you go. Solve that. First, let's get rid of the negative sign, right? Did I get it right? No, not here. You gotta get rid of here. Get rid of the negative sign. and like that. Go. And that's what we get for the difference in potential energy. Okay? That's what we get for the difference in potential energy. Okay. Now, there's a way to simplify. Here you go. That's the equation for the difference in potential energy. And I'm gonna go even further. Here you go. This delta U can be written down in terms of what? U final minus U initial. That's how we write the delta U. Difference, I'm going to, here you go, difference in potential energy. There is a way to simplify this equation. Okay, there's a way to simplify this equation. How do we simplify this equation? Okay, we take, you know, U naught as the potential energy at a reference spot. Okay, at this reference spot, which still I still do not know, U naught is equal to what? U naught, we make it equal to 0. It's like I said, it's never, when you talk about potential energy, this is a misnomer. It's not potential energy. It's always and has ever been difference in potential energy. Always. It just happens that we want to save our effort instead of writing down or speaking in terms of difference in potential energy, we just shorten it to potential energy. Okay? So here we go. We take U naught as the potential energy at the reference spot. The question here is where this reference spot is. Okay? That's the question here. The reference spot depends on the equation for the potential energy. Okay, the reference spot depends on the equation for the potential energy, for the difference in potential energy. Okay, so here you go. I mark this guy as being my reference potential energy. And where are we going to choose this spot? We are going to choose this spot at R naught g equal to infinity, to a point that's very far away from the other charge. Okay? This reference spot is chosen for R naught, at is chosen at R naught let's see if I can get it further. Here you go. At a point that's very far away from the first charge. Again, the right way to do it, to denote it mathematically, is to put the symbol here. Whenever R naught is very far away from the other charge, the equation, the difference of potential energy becomes dependent of only one R. We have a simpler equation. We then simplify our notation by dropping the F subscript. Or, here you go. Like that. KQQ divided by R. Yeah, we should put this guy here, upstairs, like that. Which is very similar to the gravitational potential energy that we saw in physics 37. Okay? Next step. That's the gravitational potential energy. And don't forget, that's the electric potential energy. But don't forget, that's the difference in potential energy, right? We are taking it with respect to the potential energy at points that's very distant. It's still the difference in potential energy. It just happened that we set the U naught equal to 0. Now, how the electric potential comes? Okay, electric potential comes in the following way. Remember the following, remember that the electric force, right? Remember that the electric force, I'm going to come up with a much simpler notation here. The magnitude of the electric force is something like that. And now I'm going to go back to a notation without subscript to be consistent with the drawings. Remember that the electric force is written as, okay, that the electric field is written as, here you go, the electric field of a charge Q is written as in, here you go, I'll put it, and that the electric field of a charge Q is written as. Okay? We can do the same thing for the electric potential energy and the electric potential. Okay? So here you go. If the electric potential energy is something like that, okay? If the electric potential energy is, then we can state that the potential energy of a point charge BQ is going to be given by, well, we can say that the potential, not potential, then we can say that electric potential. And by the way, electric potential energy we denote by U, electric potential we denoted by V. Be given by Here you go. And that's the one that's easier to measure with equipment out there. Okay. The unit of electric potential, okay, the unit of electric potential is what? Is the unit of energy, of electric potential energy, divided by the unit of electric charge. Okay, which is going to be what? Joules per coulomb. Okay, this thing shows up so frequently in physics that we give it a name. We call it volts, and also represented by the letter V. Okay, so that's what we are measuring in the lab. We are measuring energy per units of electric charge. Okay, and that's the unit that it is. Okay, so everything comes from, all that stuff comes from the definition of work. Here you go. I have all the derivation here. Okay, it's slightly different. Okay, what we did here was for the electric potential of a point charge. This is the electric potential of a point charge. Okay, this is the electric potential. This is the electric potential of a point charge. Okay, the unit of electric potential is volts. Okay, now you can also have electric potential energy differences due to a uniform electric field. Okay, let's do that. What's the uniform? What's the electric potential energy difference? And then the electric potential, right, for a uniform electric field. Calculate, here you go, the electric, calculate U for a uniform, oh, a uniform electric field. Okay. Given a uniform field, calculate U between points A and B in this field. Okay. So the drawing goes more like, let's see if I have it here. Yeah, here you go. Would be something like that. Let me see if I... Yeah, it would be something like that, okay? What would be the electric potential between 2 points? If we go to my... Here you go. Would be something like that. We have a uniform electric field in space. Find the electric potential between 2 points A and B separated by a distance L. Okay? How do we get that? Okay. Let's do that together. Given uniform electric field, calculate U between points A and B in these fields separated by a distance L. L. Here we go. Separated by a distance L. and we're going to do, so let's say A is right here to the left, B is right here to the right, and the field points from the right to the left, okay? So the particle is going from A to B. The field is to the left, the particle is going to the right. Okay. So how do we do that? We go ahead and use our definition of electric potential energy. Here you go. Let's take a look here. Remember, it should be electric potential energy difference, right? Electric. And by the way, the best way to do it, given a charge Q, I have to give you this information, subjected to a uniform electric field of intensity E, calculate U between points A and B, calculate U when the charge moves up the field. Let's see, given a charge subject to a uniform electric field, I'm going to put it this way, that points from the right to the left, okay? From the right to the left of, here we go, like that, of intensity E, okay? That points from the right to the left, comma, calculate U when the charge moves from the left to the right, move from the left to the right, huh? Or from point A to point B, from point A to point B at distance L. That's how you formulate this problem. Given a charge Q, subject a uniform field of intensity E that points from the right to the left, calculate U when the charge, it's not U, right, but delta U. Calculate delta U when the charge moves from the left to the right of at distance L. So we go ahead and come up with the definition, right? Here I'm gonna call, here go. It's no longer a point charge. We did for a point charge. Instead of calling R0 and RF, now I'm gonna call it point A to point B. Point A to point B, okay? Yeah, you know what? Let's see. Yeah, let's put R sub A and R sub B here. It's better this way. R sub B here. The force applied to the charge is going to be what? Is going to be Q times E. Don't forget that is a vector. E is a vector. There you go. But E is in the negative x direction. So let's say, positive x direction is from the left to the right. E is pointing the negative x direction. And that's what I'm going to write down here. Here you go. But first, oops, gotta get this guy here. And this guy here. Okay, now I can copy it. Right? I can get Q outside the integral. And I'm going to do something else too. I'm going to here write this electric field as minus E in the x hat direction. Oh, here you go. That's the one I want. Like that. We go ahead and do the dot product. Right, but before doing the dot product, let's cancel out the negatives here. When we do the dot product, we end up with the x right in here, because the s vector has x, y, and z components. And once we change the integrating variable, we also change the integrating limits. As I mentioned to you, the electric force is a conservative force, so I don't have to worry about the path. Next, the electric field is uniform, consequently it can be taken out of the integral. This integral is easy to calculate, so what's that gonna be? It's going to be, here you go, xb minus xa. What is known is the distance between those 2 points. xb is greater than xa, so there is no negative sign there, right? So I'm going to put it L. That's the electric potential energy difference of a charge Q subjected to a uniform electric field. 6:43, we can go another 7 minutes. Okay, giving a charge Q subject to a uniform electric field of it that points from the right to the left. Calculate delta U when the charge moves from the left to the right, or from point A to B. Okay, at distance L. Okay, if the charge is positive, then the charge gains potential energy. Then delta, here you go. If charge, here you go. If the charge is positive, then delta U is positive, and the charge gains potential energy. Similarly, if the charge is negative, then delta U is less than 0, and the charge loses potential energy. Every time that something loses potential energy, that's because it's moving according to the direction of the force. Okay, of the field. Now let's do it. Next one. What is the electric potential difference? Electric potential, not energy, but the electric potential difference of the electric field from point A to B. Okay, so we go ahead and we use the definition of electric potential Here you go. we can write down, not only V is equal to U over Q, but delta V is equal to delta U over Q. So here you go. Delta U over Q is QEL divided by Q, right? And all we get is EL. So the electric potential increases linearly with the distance. Is that what you got for the experiment? The first experiment that we got? Did you get the electric potential increases linearly with the distance from the two plates? You did, right? It was a straight line when you plot V against X. Okay? We can even, do in the following way. Here you go. Instead of getting this thing as being L, we can even here write it in a different way. Here you go. XB minus XA, right? Here you go. So let's say XA is the position of the negative plate. Okay? Let's say from the previous, what time is that? 6:47, 3 more minutes, huh? From the previous equation, let us say X sub A is the position of the negative plate, right? Going back to our drawing right in here. Here you go. We see the field pointing from the right to the left. So let's say we set XA right in here at this guy, just like we did in our experiment. The x-axis runs from the left to the right. The x-axis runs from the left to the right, just like we did in our experiment. Here you go. I'm gonna do like that, but then I'm gonna change the color to black so you don't mix up the x-axis here. Here you go. How are we doing here with time? 2 more minutes to go. Black. Okay? We did that in the experiment, right? So here you go. I'm gonna put it a label here, X. Use the label X. Yeah. 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 And like we did there in the experiment, we set the origin of the axis right in here at the inner surface of the electrode, right? So I make it this one equal to XA. And just like we did in the experiment, here is going to be electric potential equal to 0. Okay? So the electric potential increases in the opposite direction of the electric field. See that? So here we go. From the previous equation, let's say XA is the position of the negative plate that we set at 0. Then we get something like that. Here we go. UA minus UB minus UA is the final position, is the final electric potential minus the initial electric potential. The electric potential, the initial position. Okay? So you get something like that. Here you go. Alright? Set the electric potential at position A equal to 0. Okay? So it's better if we do this way. Set this one equal to 0. Better this way. right? And then set also xa equal to 0. We get something like that. And now we have this equation, ub equal to qxb, qexb, okay? Simplify the notation by dropping the subscript. But don't forget, we are taking the reference with respect to the negative plate. That's how the electric potential energy looks like. Electric potential is going to be that divided by Q. Electric potential is going to be something like that. So the electric potential increases linearly with X, just like we got there in the experiment. Is 6:51 now, right? We can stop right now. And I see you next week. When is the exam, by the way? Oh, the exam is too far away. It's gonna be at the end of this month. Okay. Close, close, and I'll see you